Welcome to springlib.
All right, so relativistic addition of velocities problem here. You have the Earth, E, in here, and two different spacecrafts moving away from it at different directions with different velocities, okay? So this is S1, spacecraft 1. This is S2, spacecraft 2. Okay, same velocity, but opposite directions. All right, so what is the velocity of one ship relative to another, and vice versa? Okay, so really the equation to use here is the relativistic addition of velocities equation, which states that u equals to v plus u prime over 1 plus vu prime over c squared. Okay, so important first step is to define reference frames. All right, so S prime will define as Earth's reference frame. S will define as reference frame of spacecraft 1, or S1. Okay, and so what this means is that v is velocity of Earth with respect to or relative to S1, or rather S2, sorry, and then u prime will be the velocity of S1 relative to the Earth. Okay? And so with this setup, we can go ahead and solve this equation for the part A. And so what we have is that u will be equal to this over this plus that over that. And so v will be 0.6c. This is because from the reference frame of S2, the Earth is moving away from it at 0.6c. And so what we've assumed here is that the positive direction is in the direction of S1, and the negative direction is in the direction of S2. And we can of course reverse this, but it will give us equivalent answers, which is to say the same relative velocities. And so working with this formulation is why we have 0.6c as the velocity of Earth with respect to spacecraft 2. This will be added to another positive 0.6c, and this is because S1 is moving away from the Earth in the direction of S1's travel at 0.6c, right? And you write out the denominator there, 0.6c times 0.6c over c squared. The c squared factor cancels, and you're left with 1.2c on the numerator and 1.38 on the denominator. What you get is something very, very close to 0.882 times the speed of light. Okay, so that's part A. Part B is the same situation, but just reversed. And so again, we have to define a new set of reference frames. S prime can be the Earth again, but now S will be S2. Okay? And so what that will give us is that V will again be velocity of Earth with respect to, in this case, it will be S1 respect to S1, and U prime will be velocity of S2 with respect to, pardon me, U prime will be velocity of S2 with respect to Earth. Awesome. So with that setup, you have that V will be negative 0.6 C. This is because from the reference frame of S1, the Earth seems to be moving away from it at the speed at which it is traveling, okay? And so that is why there's a negative there. And similarly, U prime will be negative 0.6. This is because this spacecraft 2 is moving away from the Earth at the speed at which it is traveling. So that's a negative 0.6 C. Again, these could be positive, and these here could be negative, and you would get the same relative velocities, or the same answers when you compare those two. So anyway, writing these down, you get U equals negative 0.6 C minus 0.6 C, because we just added a negative 0.6 C, over 1 plus negative 0.6 C times negative 0.6 C, right, over C squared. And so what you get is negative 1.2 C over 1.38, which works out to, you guessed it, negative 0.882 C, which is the exact answer, just with a different sign as that in part A, meaning the velocity of one spacecraft with respect to the other one will be the exact same as that of the other one with respect to it, just in different directions, which is what we expect given this problem. And that's it.